Hey guys, and welcome back to this week's video in which I'll be talking about the forms of the quadratic equation or the quadratic function. And here we'll examine three main forms, which are the standard form, the intercept form, and the vertex form. So the standard form is probably what you're most used to seeing, but as you can see, there are more forms, and each of them have their own purpose, and we'll go over what the purpose is and how that is reflected in the way that the form or function is expressed. So first let's examine the standard form, which is y equals ax squared plus bx plus c. And this is your typical quadratic equation, I would say. And what we can gain from it is, for example, knowing the concavity of the function. So for example, if we examine a, this coefficient right here, if a is greater than 0, then it's concave up, meaning it opens like this. And if it's a is less than 0, it's concave down, meaning it opens down, or like this. And this is because this is the main coefficient, and it determines as x gets very large, do we go into the negatives or do we go into the positives? And if we go into the positives, and a is positive, then we go concave up, because at very large x values or at very large negative x values, we'll be getting a very positive number. But if a is negative, we'll have a negative coefficient in front of our leading coefficient, which is going to make our function concave down. What else we can see from this form is the y-intercept, which is represented by c. Again, the y-intercept is simply when x is equal to 0, and in this case, when x is equal to 0, all of these terms would be 0, and we would just be left with c. So we can see that we have c right here. Additionally, if we work with this form a little further, we can use this equation right here to find the line of symmetry, which in this case is just the axes as I have drawn it, but in other cases that will not be always the case. And additionally, this is the form of the quadratic function for which we utilize the quadratic equation right here to find the roots. Now let's move on to the intercept form, and this is where we have a times, in brackets, x minus x1, and then close bracket, and then in the other bracket times x minus x squared, close bracket. And this is helpful in letting us see the roots. Of course, we can also see concavity based on this a right here. Again, if a is greater than 0, then we have concave up. And if a is less than 0, then we have concave down. Like always. Also, a is always the same in all of these forms, because otherwise our x squared coefficient would not be the same. So it always ends up being the same, just so you know a little trick. But the main point of this is to know the roots. And here, x minus x1 is the root, and x2 is the second root, because again, this is a quadratic, so there's always two roots, whether they're imaginary or not. Sometimes we only see one, sometimes we don't see any, but it's a polynomial to the second degree, so we're gonna have two roots in this case, and x1 is going to be our first root, x2 is going to be our second root, and why this makes sense is because as soon as x is equal to a root, part of the brackets will be 0, and this whole equation will be 0, and that's when y is equal to 0, and that's exactly what a root is. A root is the x value when y is equal to 0. So here we can see x1, 0 and x2, 0, and we are given our roots. From our roots, we can then determine the line of symmetry if we need to, and at the line of symmetry is where the vertex resides, so we could always find the vertex based on finding the line of symmetry, because the line of symmetry is, again, right in the middle of the roots. So we can represent the line of symmetry as at the point x is equal to x1 plus x2, which are the two roots, divided by 2, because they're going to be right in the middle, so in this case, right here. Now, last but not least, let's move on to the vertex form. And again, as the name suggests, this lets us see the vertex. First, let's again recognize that based on this a right here, we can see the concavity, And again, if a is greater than 0, it's going to go concave up. If a is less than 0, then it's going to go concave down. And here, the defining features are the h and the k. And the h is going to be the x value of your intercept, and the k is going to be the y value. So you're going to have this point right here, hk, at your vertex. And yes, this is mainly what this form is used for. Now, when performing calculations, often you are required to switch between these, and there are different methods to do so, but my biggest tip would be if you have the standard form and you want to switch to another form. For example, if you want to switch to the intercept form, of course you can rearrange using just plain algebra if you have an intuition for it. But what I recommend, if you do not have the intuition for it, is to, for example, find the intercept using this equation, and then write this as a times x minus negative b, for example, plus blah 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 over 2a times x minus negative b minus square root of delta over 2a. Sorry, this can be a delta right here as well. For example, this is how you can convert from standard into intercept form. How you can convert from standard into the vertex form is you find your line of symmetry or your equation for symmetry, and we know that the vertex form is going to have the x-coordinate of the vertex inside the brackets. So this is going to be our x-coordinate of the vertex, because our x-coordinate of the vertex is always at the line of symmetry. So we can just write that our equation is equal to a times x minus negative b over 2a squared plus, and then you take the y value using this y of negative b over 2a, and that's going to be your coordinate. Again, all we're doing is we're finding the vertex using this formula right here, and then we're implementing it by writing it in the form we have seen over here. Switching between these two, I would suggest expanding and then following the steps that I've just shown previously. And either way, you can always just try to manipulate it algebraically if you want to return to the standard form. So to summarize really fast, here our c is going to be our y-intercept. This is going to be our root 2 or root 1, doesn't really matter. This is going to be our root 1 or 2 either, doesn't matter. And for this one, we can say that hk is the vertex. So this is a very nice summary of all of the different forms and the very basic reason for why we use them. So I hope you learned a little bit more about quadratics, how we express them, and what each expression means, and tell us how each expression is sometimes useful, sometimes not so useful. For example, if you want to know the intercept, the y-intercept, it would be a lot more useful to have this standard form right here. But if you wanted to know the roots, it would take you so much less work, and you could just look at the graph and the equation if you use the intercept form, which shows you the roots. On the other hand, if you wanted to know the vertex, you would not have to do a single calculation if you had your function in the vertex form. So this is why we have all these different forms for the quadratic, and I hope you enjoyed. I hope you learned something new, and see you next time.